Alright, welcome back to chemistry. We have finished talking about kind of our introductory math stuff, essentially. We're going to go ahead and start talking about atoms and compounds now. So we're going to just start moving ahead with talking about things kind of on the atomic and subatomic level here. So, atoms. These are kind of, as the Greeks had the idea, that these are kind of the smallest unit of matter that you can have. And not a unit like kilojoules or something, but a unit as in like a chunk. So the smallest chunk of matter that you can have. And, I'm going to quickly kind of just gloss over this. We know that atoms are made of protons, neutrons, and electrons. And those are called subatomic particles. We see that protons are positively charged. They have a mass of about 1 AMU, 1 atomic mass unit. And they're in the nucleus of the atom. We know that neutrons are neutral, about 1 AMU. They're a little bit heavier, a little bit more massive than protons are, but that's neither here nor there. And then electrons are negative charged. They have a mass of 1 over 2000 AMU, so 0.0005 AMU, so very, very small. And they are in orbitals around the nucleus. Or, as you'll probably have remembered from, middle school or whatever, you might think of them as orbits. You might have seen something like this, where you have a nucleus and kind of, electrons around it and, that sort of thing. This bit here is the nucleus. And this sort of, these dots around it are electrons. And this is called the Bohr model of the atom. That's the one that you've seen, where electrons are kind of just circularly going around. We're going to talk about in chapter 6 or 7, about more sophisticated models of this idea. But this is a good place to start. We have our nucleus in the middle that has our protons and neutrons in it, and then we have the electrons kind of zipping around it. As we see that the protons and neutrons are much more massive than the electrons are, we typically ignore electron mass in discussing things. And it's kind of an interesting comparison here, because the radius of the atom over the radius of the nucleus is somewhere along the order of 10 to the 15th power. So what is that? Quadrillion? Yeah. So the atom itself is a quadrillion times bigger than the nucleus is. So the nucleus is tiny. And yet the nucleus has almost all of the mass of the atom. 99.999% of the mass of an atom is in the nucleus. So if you want to think about the size difference there, we're talking about the nucleus being 1 grain of sand on the pitcher's mound in Dodger Stadium, where Dodger Stadium is the atom. That 1 grain of sand in it is our nucleus. And imagine that the entire mass of that is that 1 grain of sand. And so most of the atom is empty space, right? A huge amount of empty space. And so it's just curious to think about that, right? So we have this incredibly dense nucleus, tons of mass right there in this little speck. And we have the atom being, by and large, empty space. 99.99999999999% empty space. So that's all we are. We are just a bunch of empty space, hoping that an electron is going to come move through us, right? So very, very profound difference there. So a couple things we talk about with atoms. We know that the number of protons determines the element. So for example, carbon has 6 protons. All carbon atoms do. All fluorine atoms, they have 9 protons each. This is called the atomic number. And how the heck are we going to know these? Don't ever memorize things like that, by the way. But, oh no, I do not want to update. Okay, or upgrade rather. I will use the free version. We see here carbon has this number 6 on it. Fluorine has the number 9 on it. That's where I've got those numbers from. So for every element, we're going to have an atomic number and a symbol for it. So 1 or 2 letters. First letter is always capitalized. Second letter, if there is one, is always lowercase. Those are kind of our symbols for the elements. And we can see that this periodic table is kind of arranged in atomic number order. So we can see very clearly the number of protons in every element. So an element is defined as having atoms with the same number of protons. So every single carbon atom has 6 protons. We can find this number on the periodic table. We're going to see the number of neutrons will determine which isotope of an element you've got. So isotopes are atoms of the same element, but they have different numbers of neutrons. For example, carbon has 3 primary isotopes. There's no way to tell, by the way, at least for you guys, how many isotopes a particular element will have. Some have 1 stable isotope. Some have 30. Is there a way to predict which ones will be stable? Not for you guys. Not until really advanced chemistry, actually. Advanced nuclear chemistry is where you'll investigate that sort of thing. But in kind of us, in general chemistry, no. We just need to know that isotopes exist. We know that in order for an atom to be stable, there have to be neutrons if there's going to be more than 1 proton. The reason for this? Well, it's simple. All the protons are within the nucleus, right? And all protons are positively charged. And so we know positive charges repel each other, right? They don't want to be next to each other. So what neutrons do is they create something called the strong force, or strong nuclear force. And that's what actually holds the nucleus together. So, because the protons don't want to be together, right? They repel each other. They have the same charge. So neutrons generate the strong force. And in physics, that's one of your 4 fundamental forces, right? You have gravitation, strong force, weak force, and what's the 4th force? Is it electrostatics? Oh no, how embarrassing. Let's find out. Let's Wikipedia this. 4 fundamental forces. It is electromagnetic. Okay, good. I wasn't crazy. So, the strong force is called the strong force. The physicists have very good naming skills, right? And the strong force is stronger than electrostatic repulsion. And therefore, you can stick in your nucleus all these positive bits together. Oh my goodness. 1 second. I accidentally locked it. There we go. So, in your nucleus, you've got all these fun things. Some of them are positive, right? Those would be the protons. Some of them are neutral, which are the neutrons. The neutrons are there gluing everything together with their strong force. So they are there sticking everything together so that your protons do not repel each other. So they are held together there by that strong force created by the neutrons. So typically, the number of neutrons is greater or equal to the number of protons. Typically. And we're going to see, in fact, as we get to heavier elements, sometimes you need twice as many neutrons as protons. So just things, as the number of protons get bigger, you need more and more neutrons to keep them in check. So though in the smaller ones, it's usually just equal number is fine or a little bit above is fine. You typically don't have many that are below. You have it. There is helium-3, which has 2 protons, 1 neutron, but that's not a very good example. It doesn't. There's not a lot of that around. So, just typically your neutrons is going to be bigger than protons, and we have a way of describing them. The mass number of an isotope is protons plus neutrons. And we will typically, what am I writing 6 for? 12, 13, 14. These are mass numbers, which is given the letter A, because that makes sense. It's protons plus neutrons, the number of them. And that's that number in the corner there. So mass number is protons plus neutrons. That you have in your particular atom. So these 3 kind of flavors of carbon exist. All carbons, remember, all carbon atoms have 6 protons. Otherwise, they would not be carbon atoms. They would be something else if they had a different number. So, if we kind of just put that there, we see, aha! Well, this first one has got 6 neutrons. This one has 7. And this one has 8. Since that mass number on top is protons plus neutrons, these all have 6 protons because they're all carbons. And so we can see these 3 flavors of carbons called isotopes of each other have different numbers of neutrons. Very exciting. By the way, this business of 6 protons, which remember is called the atomic number, is given by the letter Z. Because A, of course, is for mass number, But Z makes more sense for atomic number, which starts with the letter A. I don't know why they did this, but atomic number is abbreviated Z, and mass number is abbreviated A. So, go figure. These are typically arranged. Oops. Like so, where you have your mass number, which is protons plus neutrons. Z is your atomic number, which is your number of protons. This guy here is your elemental symbol, like C for carbon, or He for helium, whatever element you're looking at. One part here that's not given, this is where we'll indicate the charge of something. And we'll talk about charge a little bit later on, just because the book does it that way for some reason, and so we'll postpone that for right now. We're going to see that we can get the atomic number from the periodic table. We can get this atomic number from the periodic table, but if we take a look at our periodic table, let's say we're looking at carbon. Okay, apparently I've got to touch it. There we go. I've told you that carbon comes with those wonderful numbers 12, 13, 14. However, we don't really have that here. Right, do you see the number 12, 13, or 14 here? Kind of. We see 12.01, right? Bad example. Here, let's look at bromine. That's one of my favorites to look at. So bromine. Bromine comes with the number 35 for its atomic number. And it comes with this other number, 79.9. And I'm not sure where that would come from, but let's go ahead and write these things down. Oh, I don't need that. So bromine, 79.9. Where did that come from? In fact, I'll write it a little bigger. Was it 35? We see this on our periodic table. Let's. When in doubt, let's question Wikipedia. That's kind of my go-to. Let's take a look at Wikipedia. What does Wikipedia have to say about bromine? I'm going to skip down. Oh, what's this? We have 2 isotopes of bromine. Bromine comes in 2 flavors. Bromine 79, which is 51% of all bromine, and bromine 81, which is 49% of bromine. But if I look on the periodic table, I saw neither of those numbers. I didn't see 79, I didn't see 81. I found actually something close to 80. Right? I did not see either of these numbers distinctly. I got 79.9. But wait. If we look at these, whoops, totally on the wrong side. I'm sorry, I'm looking at these things over here, yeah? This bromine 79, if that's 51% of bromine, and the other 49% of bromine atoms are bromine 81, just the naturally occurring rate of bromine isotopes. Well, I mean, if we kind of take a look at the average, well, that's going to be around 80, but maybe a little bit closer to 79, because 79 is a little bit more, right? So, that's curious. Let's see if we can't work with these numbers. Let's see if we can't work with those numbers. So bromine comes as 2 different types. This one is about 49%. This one's about 51%. And we see here, we have again this number from our periodic table, 79.9. Well, let's just try averaging those together. Well, that would equal 80, right? And that's not quite what we're looking for, is it? And so we can't say, okay, it's not going to be a simple average. But we have this idea of the abundance, which we were able to find on our handy-dandy Wikipedia table. And so, let's try and factor that in to this. And say, okay, well, we know if this bromine 79 business is about 51%. Let's just put that in decimal form. And our bromine 81 is about 49%. Let's see what happens if we do this. Let's do the math here. So 79 times 0.51 plus 81 times 0.49. Oh, 79 point. Technically 98, but we'll be okay with this. Indeed. The reason we don't get the number we're looking for, by the way, I will explain. Is because these are mass numbers. So remember, mass number is protons plus neutrons, right? So we looked at this isotope and we said, okay, well, we know it has 35 protons. This isotope must have, I can do this math. 79 minus 35, 44. 44 neutrons. The other one has 46 neutrons. These are mass numbers. And those are exact numbers because we're counting numbers of protons and neutrons. You can't have half a neutron. They come as discrete numbers. So, but what's interesting though, is because protons weigh actually a little bit less than neutrons, just a little bit, we're going to see that the actual mass of the bromine 79 isotope, again, this is not something you'll ever need to calculate or anything, I'll give this to you, is 78.91834 AMU, atomic mass units. So we see it's actually just a little bit less than 79 because the atomic mass unit is what is a neutron, but protons weigh just a little bit less. So that's why our number is slightly less than 79. And we're going to see that the actual mass of bromine 81 is also slightly less, 80.91629 AMU. Someone has weighed all these things out. Good for them. They're crazy. Okay, let's go ahead and take a look at these. Let's try these numbers instead. So these were mass numbers, those were just kind of, we added the number of protons plus the number of neutrons. This is an approximation. So, but let's try it now. Let's do the same thing, but with our real numbers. So, if we try this, 78.91834 times 51% plus 80.91629 times 49%. I hope this gives us the right number. 78.91834 times 0.51 plus 80.91629 times 0.49. Oh ho, and what do we get? 79.91629 0.89, which we can round to 79.90, which is, lo and behold, what we have as our what's called atomic mass. That's the number on the periodic table. So this number is the atomic mass, and that is the weighted average of all isotopes of an element. So, if we were to take 100 atoms of bromine, statistically we'd say, okay, 51 of those atoms are bromine 79, 49 of those atoms are bromine 81. However, what's the average mass of any one atom that I pull out? If I were to equalize them all, take the entire mass of those 100 atoms and divide it by 100 equally, we would see that we would get 79.9 as our average. Again, this is not done on hundreds of atoms. We're going to see that we have quintillions of atoms that we deal with. And so our statistics become more and more relevant there. So we're going to see that this weighted average works out very, very nicely, especially when we get to such huge numbers, such huge sample size, 10 to the 23rd power. So huge numbers of atoms we're going to be dealing with. So this atomic mass idea works out nicely. If we want to put this in formula form, we can do so like this. Sigma notation just means you add them all up. So however many isotopes there are, you'll multiply the mass of the isotope times its abundance in decimal form. Not percent, so put it in decimal form. And you'll add that up for however many there are. So for bromine, there were 2 isotopes. So we would add up 2 things. We're going to add the isotope mass of our first isotope times our abundance, added to the isotope mass of our second one times the abundance there. So that's how we're going to calculate our atomic mass. And so for something like, let's see, let's choose an element. How about xenon? Let's see, how many isotopes does xenon have? Hopefully more than 2. Oh, wonderful. Tons of isotopes. Okay, back to Wikipedia. Looking at xenon, look at all these isotopes we have. We typically don't deal with synthetic ones. We only deal with natural ones because we're looking at natural isotopes of these things. So 1, 2, 3, 4, 5, 6, 7, 8, 9 different isotopes of xenon. All of those are going to have their own isotope mass, not given on this thing here because this is just mass numbers, as well as an abundance. And so if we wanted to find the atomic mass of xenon, we would have to add up 9 products. We'd have to multiply whatever the mass of xenon 124 is, multiplied by 0.00095, plus the mass of this one times 0.00089, plus etc. all the way down. Let's see if we can't find the half-life, decay mode. No, we don't need these. Look at how many isotopes there are. So I'm going to zoom out here. Aha! No, never mind. These are just natural abundances. Isotope mass. Perfect. Okay. So I guess this was our first one, 124, right? So here's our isotope mass. So we would multiply this number by the abundance. This is already in a decimal, it looks like, so that's great. We would add up all of these numbers. So the 0.26 times this number here, we would add up all of these things, and we would end up getting our atomic mass this way. So you see how many isotopes there are. Many of them are synthetic. They're created in a lab. They don't really exist in nature, so we don't have to worry about them. So, but there you have it. So you see these numbers are not just made up. Wouldn't that be nice? There are reasons for all of these things. And so that number that you're going to see on the periodic table there is your atomic mass, and that is your average of all of the isotopes with their abundance factored in. So that's where we get those numbers. Wow. I have just talked for like 30 minutes straight. Are there any questions on anything that we've talked about so far? Okay. So, let's talk about compounds then. So, compounds. Compounds, as we know, are made of more than one element. We're going to use the atomic mass and all that stuff later on. Is there a term for a non-isotope? Can you clarify that, Michaela? So isotopes are just words we would use to compare different, same element but different number of neutrons. So isotope is always kind of just used as a term to compare one specific atom with another. So everything is an isotope. Okay, that's what I thought. Okay, so each element has a certain number of isotopes, and they are all called isotopes of that element. So we would say that are isotopes of bromine. And we would say that what's chromium I'm thinking of? No, is it cobalt? It's cobalt. Is the only isotope of cobalt. And I'm not lying, cobalt only has one stable isotope. So the term can be used even if there's just one. So it's when we are looking at atoms, we typically are not looking at specific isotopes. We just say we're looking at all these quintillions of atoms, we're just going to average them to be our atomic mass, and we don't even worry about isotopes anymore. However, if we wanted to look specifically at one type of that element, we can then talk about isotopes. So it's looking farther into it than we normally would. And so it's looking specifically at individual atoms that we would talk about isotopes. But since we mostly talk about things kind of en masse, where we have all of the atoms at the same time, we don't typically talk about individual isotopes. Okay, cool. Good question. Okay, where were we? Okay, so compounds are made of more than one element. And just for fun, all of those elements will have their own numbers of isotopes and isotope flavors and all that. We're going to see, for example, here is a compound. Actually, let me, I'm going to actually just move this down just so we don't do that. Oh, gosh. Okay. Let's put a line here. There we go. Okay, so compounds are made of more than one element. This little thing here is what's called a chemical formula. And it tells us we have 2 hydrogen atoms plus 1 oxygen atom. Technically, if we really wanted, we could say H2O1. No one does that. Don't do it. As chemists, we avoid redundancy whenever possible because we are weird that way. So if there's only one of an element, we just don't write a number. If nothing's written, we assume it to be 1. We're going to see that all water molecules have this formula. So if we have a sample of water molecules, every single one of them is going to have 2 hydrogens and 1 oxygen. There's a fancy, I think, law for this. I think it's called the law of constant composition. And that, I mean, it's really kind of a formal way of saying that every single water molecule has exactly 2 hydrogens and exactly 1 oxygen. So when we're looking at a chemical formula, every single unit of that, whatever it is, if it's sugar we're looking at, every sugar molecule, if it's salt, every unit of salt has the same elemental composition for it to be a compound. So the ratios are fixed there. So each water has two hydrogens, 1 oxygen, no other things. If we have something like this is not the same thing as water. That's hydrogen peroxide, the one on the left, versus water. So we distinguish different things from each other by using chemical formulas. All right, so chemical formulas there tell us how many atoms and what type of atoms we have. So we have hydrogens and oxygens in this one. The number of those, however many we have of all of those, is going to be constant for every unit of that we have. So every hydrogen peroxide molecule has 2 hydrogens, 2 oxygens. Every glucose molecule has 6 carbons, 12 hydrogens, 6 oxygens. So they're all the same. Every single glucose is like this. One more thing to note, however, fructose also has the same formula. So, what's important to note here, and here, let's do another one. We have also, galactose, another sugar, also has the same formula. In fact, there are 16 different sugars that all have the same formula. Sometimes we're going to see that molecules have the same but different arrangement. Of the atoms. And, well, I'm not going to throw all of these are organic molecules, they're a little bit more complex than stuff we're going to deal with in this class. But suffice it to say, these take different structures. They're arranged in different ways from each other. And in doing so, we end up with different molecules. But every glucose molecule is exactly the same. All glucose molecules have the same arrangement as all other glucose molecules. And all galactose ones will have the same arrangement as all other galactoses. So in this case, we have the same number and type of atoms, but they're arranged differently. These are called isomers. And there's your definition. So they have the same formula, but there's different arrangements there. And so those would be called isomers of each other. And in fact, there's... Okay, that's enough. I don't need to go further in detail with that. Yeah, fine, I'll tell you. They're also called epimers because these are specific types of isomers. You have all these different types that you're going to learn in organic chemistry that will make you cry. So, just a hint of what's to come when you take OChem. Yeah, it makes sense. They don't affect anything in the compound. So isotopes do not affect the chemistry of... Okay, I can't say that. They have very, very minor effects upon the chemistry of a compound. In organic chemistry, we'll see a few instances where we have deuterium instead of regular hydrogen that make a chemical difference. But in this class, it does not matter. So for us, we don't have to worry about isotopes beyond kind of acknowledging they exist and then understanding that we take into account all of the isotopes when we talk about atomic mass. So, for example, you could have... Let's see how best to explain this. So, let's say in a chemical reaction, you're using water to react with something. And let's say that something you have has it has an oxygen in it. So let's say we're gonna okay, we're going way beyond the scope of this class, but I like your question. We'll deal with it. We're gonna take this organic compound and react it with water. And we know what happens is we end up getting this out. And so, if we wanted to track where this oxygen is going, if we wanted to see, okay, well now we have 3 oxygens here, do we end up switching any oxygens out? Where does the oxygen from the water end up? So, it turns out it ends up here, by the way. Or it could end up... anyways, we'll say it ends up there, but how do we know that? How do we know where does this oxygen end up? The only way for us to distinguish different oxygens from each other is to pay a lot of money to some company which will have purified one isotope of this. So oxygen typically comes as oxygen 16. Here, let's go back to Wikipedia for a second. Okay. So, oxygen. By and large, almost 100% of oxygen is oxygen 16. However, by using centrifuges, very, very advanced centrifuges, we can actually separate water that has the oxygen with the 18 on it, this particular isotope. And by isolating it, we can now say, okay, again, we've paid a lot of money for this. It is not cheap to separate isotopes. We're going to see that's why it's very difficult to enrich uranium. It's the same idea. But to get one particular isotope, if we wanted to get every water molecule with oxygen 18, so that we could see later on, well, we know most oxygen is oxygen 16. So we have techniques to say, okay, I've paid a lot of money for this oxygen 18. I'll put this in black so we have those. And so if we want to understand how the chemistry of this reaction is taking place, we can isotopically label one of these atoms. So by specifically introducing only water molecules that have the oxygen 18 isotope, we can then analyze the two molecules we get at the end of this reaction and be like, okay, where did this oxygen end up? Aha, it's part of this compound on the left. Now we know more about the chemistry of what's happening, how that water is interacting with the compound on the left there. So it's very important for determining how molecules react together. We can use the difference in isotopes to do that. So it's certainly got its utility there. We also have, for example, carbon dating. So, organisms breathe in, breathe out. We breathe out carbon dioxide as we exist, right? We also consume carbon in the form of glucose and fats and proteins and that sort of thing. And we metabolize that carbon, right? Once we die, however, our carbon doesn't turn into carbon dioxide anymore. We don't breathe it out. So all of the carbon that we die with stays with us. And it turns out that carbon-14 actually just decays over time. And since we know how much carbon-14 is in the universe, proportionally speaking, if carbon-14 is 1% of all carbon, which I think it's less than that, but you can take a sample of something dead, a fossil, and see what proportion of carbon-14 it has. And you can see, okay, well, I know that carbon-14 decays at a rate of 5,000 years, or it takes 5,000 years for half of my carbon-14 to disintegrate. And so by looking at the amount you have versus the amount you would have had when you were alive, you can see how long something's been dead. And that works for things that have been dead for, 20,000, 30,000 years. So you can use isotopes that way as well. All right, but in terms of chemistry, whether or not this oxygen in the water is 16 or 18, they're both going to react the same way. So in terms of chemical reactions, they do the same things, though there may be slight differences in rate or something else, minor differences that we don't have to worry about here. Okay? Again, very, very good question. It's cool stuff, yeah. Awesome. Okay, so, anyways, chemical formulas, yes, that's what we're talking about. I'll just put tangent here. Okay. We're going to see things can have molecular formulas or empirical formulas. And all of these, for example, some of the compounds we've talked about, we're going to see that those would describe the number of atoms in a particular molecule. So we're looking at one molecule, it's got all of these atoms connected together. However, when we were first kind of doing kind of rudimentary testing to find out what something is, oftentimes we would burn it. And so by burning it, we would say, okay, we're able to isolate different compounds after we burn it. And suffice it to say, we're able to say, okay, well, I know that my compound is, 89% oxygen and 11% hydrogen by mass or something. We'll talk about this later on. And by doing some math, we'll see, aha, well, I know the ratio of oxygen atoms to hydrogen atoms now is 2-to-1. Did I say hydrogen first? Well, suffice it to say, if we did that, we found out, okay, well, I know my ratio of hydrogen to oxygen is 2-to-1. An empirical formula is always the lowest ratio you can have. So for example, our H2O2, just empirically, that means using experiments, we would be able to determine that the ratio of hydrogen to oxygen is 1:1. By using other things, we'll be able to get 2:2. But the lowest ratio is what's called an empirical formula. It's the lowest ratio of atoms to each other. And if we look at the top example, the glucose, or any of those sugars, they all kind of have some multiple of CH2O. So 1 carbon for 2 hydrogens for 1 oxygen. And those are called empirical formulas. Those are the lowest ratio. These are things that we can find out experimentally pretty easily. We can find out the empirical formula of a compound very easily. However, by more detailed analysis, we can say, wait a second, we actually have a bigger molecule than our empirical formula would suggest, and so we must have some multiple of that. Sometimes your empirical formula and molecular formula are the same, like with water. It already has the lowest ratio, 2:1. Sometimes it's not, so that'll work. Notice that another one we have, that's formaldehyde there. Its empirical formula is also CH2O. So things can definitely have the same empirical formula. We're going to see that, in fact, carbohydrates in general typically have the same empirical formula as each other. And there's hundreds of different carbohydrates. You've got ribose, part of your RNA, that has the empirical formula CH2O. If you were to burn ribose, you would see that you would get the ratio of 1 carbon to 2 hydrogens to 1 oxygen in there. Formaldehyde, same idea. These things have nothing to do with each other, glucose and formaldehyde, but they happen to have the same empirical formula. And so just some interesting bits there. So there's just some terminology that we have. So an empirical formula for a compound is the lowest ratio of atoms that you have. A molecular formula tells you more about specifically that molecule. So every glucose has 6 carbons that are bound to each other. We'll talk about chemical bonding in chapters 8 and 9, I think, where we talk about that. And so we can have multiples of these empirical formulas that make molecular formulas. And these can also be using more experimental data determined. So, fun stuff, I suppose. Okay, cool. Terminology over. Let's talk about ions now. Okay, ions are charged atoms. And what we mean by charge is that they have an unequal number of protons and electrons. So, sometimes in certain elements, you'll have unequal numbers of protons and protons and electrons within your atoms. So for example, if you have calcium, if calcium is neutral, it will have 20 protons and 20 electrons. Very exciting. It has the same number of both. We know protons have a charge of +1. And we know that electrons have a charge of -1. If we add those together, we get 0. It's neutral. However, very often, we see that calcium likes to take the charge of +2, which as chemists we write as 2+. In biology or other things, sometimes you see these. No, we don't do that here. So for chemistry, we only ever use that left one, where we put the number of the charge, the magnitude of it, followed by the sign of it. So a little bit unusual, but that's the way we do it. So you're going to want to get in that idea of doing number and then the sign afterwards. And we do indicate positive and negative. So we don't just write Ca2, right? We're going to write 2+ to indicate it's a positive charge. Anyways, so this means, remember, all calciums have to have 20 protons. And if we think about it, this calcium 2+, we're going to see that the only thing that's charged other than protons, and protons cannot change, are electrons. And we're going to see most chemistry that we talk about deals with movement of electrons. So electrons are more free to move. They're zipping around the atom, right? So they can just leave if they want, or new ones can come in. And we're going to see if it's 2+, well, that's more positive than the neutral one would be, right? And if we're more positive and we can't add more positive things, we can't add protons in, well, we could get rid of some electrons. If we lose negative things, we become more positive. So if we want to be too positive, we have to lose 2 electrons. And so we're going to end up having 20 minus 2 electrons in there, so 18. We can think about it this way. The charge is your number of protons minus your number of electrons. That'll give you the charge of it. So sometimes you'll have more electrons than protons. That'll give you a negative charge. Sometimes you'll have fewer. That'll give you a positive charge. Or you can have 0, which will be neutral. So we're going to see, just in general, ions come in 2 types. We call them cations. Cations. These are positive ions. And things have lost electrons. In order to be positive, you've lost electrons. So you've given them away, or something has taken them from you. You're a cation. On the other side, we have anions, which are negative ions, and those have gained electrons. So normally, every element has the same number of protons and electrons, but we're going to see electrons can move around. Sometimes you'll gain some, sometimes you'll lose some. And we're going to see there are trends here that we can talk about, that the periodic table is going to help us to do. Speaking of which, let's do that. We're going to see that there are trends that we're going to be able to see on our periodic table here for preferred charges. We're going to see that there are certain numbers of electrons that are particularly desirable. And unfortunately, this is not something we're going to really talk about until Chapter 7, when we look at this a lot more closely. But suffice it to say, here in Chapter 2, we are just going to learn some patterns of preferred charges. And that's kind of as far as we're going to go. So suffice it to say, there are certain numbers that are desirable, and there, as a result, atoms will either gain or lose electrons in order to reach that number. So they'll just kind of move the closest way. So we're going to see periodic table here as I've drawn it. You know, here's our hydrogen, here's our helium, here's our lithium and beryllium, and so on. I'm not going to write them all out because I don't need to do that. We can just put some numbers on these. We typically talk about, in this class, these 8 groups. Sometimes you'll see these with the letter A after them. Or you might see 13, 14, 15, 16, 17, 18. Either way, whichever way you like to learn them. I mean, your periodic table will have it whatever way your periodic table has it. So, if I look at this OChem book, for example, oh my god, it doesn't even have a periodic table. So, apparently we don't use no, it does. Okay. So, this one, in fact, periodic table here. This one actually has both, so it's written, 13 or 3A. So you have both of them on there. So, periodic table. You'll probably want one of those. Find one you like. Print it out. Keep it. It'll be your friend. With these, we're going to see that elements in the same column as each other, which we call groups, and we see that those behave similarly to each other. The rows on the periodic table are called periods, and that's as far as we're going to take it until chapter 7. There are 7 periods here. Sometimes on a periodic table you'll see a chunk taken out and put on the bottom. That chunk goes, it's like really right here, but we take it out so we can condense the table and make it not so big. So, but suffice it to say, let's get rid of that. That's not important for us right now. Okay. So, the elements are arranged in columns and rows, right? We're going to see that things in the same column tend to behave the same way. And specifically for our purposes here, they tend to form the same charge as each other. They try to find the same charge. So, we're going to see, if we look at these columns, things in this column tend to form a +1 charge. Things in this one tend to form a +2 charge. Those are the numbers of electrons that they like to lose in order to become happy. So things in that first column tend to lose 1 electron when reacting. And things in the second column tend to lose 2 electrons. Now hold up, it seems I've frozen my face. Does this still work if I squiggle? Let's see. It does, okay. I don't know why my face is frozen. And it's frozen in this terrible position. Okay, here, let's try this. Let me turn off that. Still frozen. Okay, well, whatever. I'm gone, apparently. That's okay, you don't need me here. We'll see if it starts working again in a second. But suffice it to say that things in that group 1, so something like lithium, sodium, potassium, those all prefer a +1 charge. Things in group 2 will often see with a +2 charge. We're going to see that these elements don't really form other charges. I say that because this thing in the middle, oh my gosh, go away. No. For now, that block in the middle, they make all sorts of charges. All sorts. We're going to skip it for now. Moving on, let's actually go to the end and work backwards. just make my columns here. Okay, there we go. We're going to see that things in group 18 don't make charges, ever. In normal life, they do not make charges. Things in group 7 tend to make -1. Things in group 6 tend to make -2. And things in group 5 tend to make -3. So, patterns here. Those things are all gaining electrons, right? And they're all kind of moving towards that column 8, right? They like the numbers of electrons that are found in column 8. Those are the happy numbers. We're going to see generally things in group 3 tend to make +3 as well. And then finally, we don't really see group 4 stuff making ions, but they do exist. Sometimes they're either way, but they're not common. So you could see them as plus or minus, but they're uncommon. One other exception that we have is hydrogen. Hydrogen is special because it can go either way. Hydrogen can go either +1 or -1. It's happy to do either one. So even though it is in group 1, it still does -1. If we look at group 3, stuff like aluminum will give you 3+ charge. Nitrogen and phosphorus tend to take -3. Oxygen and sulfur -2. All of these guys take -1 as their preferred charge. So they're all grouped together in their nice little columns, and they tell us good things about, or they all have preferred charges. Let's test the video again. Still frozen. How annoying. Okay, well, I give up. The next 17 minutes you're not going to see me. Okay. We have names for these, by the way. Group 1 is called the alkali metals. Group 2 is called alkaline earth metals. Group 7 are called halogens. Group 6, while it is less common, are called chalcogens. And group 8, which don't take charges. Remember, we got some of them. Those are called noble gases. These are just examples from each group, along with the charges that they take. These groups have names. So, again, because things in a group tend to behave similarly, we see these all form the same charges, preferred. All the halogens act the same way, so we have group names for them. So again, groups are columns, and so we have names for some of them as well. If we look at the periodic table again, just put a couple of things here, and I'm going to in fact now include our thing on the bottom. Generally speaking, these are called main group elements. Main group elements on the other side as well. So those there as well. main group elements. These here are called transition metals. And these are called inner transition metals. So just some kind of categories here. So those groups that I listed up here are all main group elements. In that middle block there, we have the transition metals. And within that, even further, are the inner transition metals, oftentimes put at the bottom of the periodic table, although they are technically parts of periods 6 and 7, the bottom two rows. They are part of that. If we were to include them, this is what the periodic table would look like if we included them there. So we just typically take it out again. So this is your main group elements. These are your transition metals. These are your inner transition metals. Again, main group elements up here. So that's where that little section goes. But as you can see, it's terribly blobby now, so it's easier to just take those out. So we typically put the inner transition metals on the bottom there. Okay. A few more things. A few transition metals will have preferred charges as well. Preferred, there we go. Preferred charges. Those would be these three. So these three you will want to learn as exceptions. So these ones do have preferred charges. They do not have multiple, but we're going to see all the other transition metals often have at least 2 preferred charges. I mean, I guess we can't say preferred because they have variable charges. So all other transition metals have variable charges. For example, most commonly you'll find iron in these 2 flavors. Iron often comes as +2 or +3. These are very common. Manganese likes a whole bunch of different types, all the way up to 7+. And it's just going to occur in different, what are called oxidation states, different charges. And so it's not going to be obvious to us right away which iron we're looking at. We'll see there are ways to tell when we're looking at a compound that's with one of these particular iron ions, what we're looking at here. So the transition metals do have variable charge. For most of them, there are 3 of them that are exceptions. And thankfully, by the way, those 3 exceptions are located right next to each other. I get better and better at drawing periodic tables as the semester goes on. I always lose it and then it comes back. So, one way people like to remember this, you have those 3 elements that are forming this diagonal line here. And you might be able to say, aha, well, 3, 2, 1. Oh, we totally cannot see that. Okay. Okay. how to write this. Okay, well, plus 2 plus 3 plus 3, 2, 1. So going diagonally down, aluminum is 3, zinc is 2, silver is 1. Diagonally down. Just a pattern. It's called a mnemonic. So just to help you remember it. 3, 2, 1. And then cadmium is also here. Kind of just thrown in there, but it's 2 plus as well, same as zinc. So those two in particular only ever take 2 plus. So just ways to remember those 3 are fixed. Alright, and aluminum you already know is going to be 3 plus, so. Alrighty. Any questions on that stuff? So preferred charges, groups, group names, kind of patterns on the table. We have more. I'll start drawing my periodic table if you guys have questions. Alrighty. So we're going to see also most things on the periodic table, including our inner transition metals, are metals. We'll talk about what that means. Things on the right side are what are called non-metals. And then things kind of along this line here that I've drawn. So, for example, boron and silicon and arsenic. No, arsenic is As. Things like this are what are called semi-metals or metalloids. Things along this line. So they can be on either side of the line. Phosphorus tends to be more non-metallic, but you can have it as a metal. So we do see these sorts of things, patterns here. So selenium are semi-metals. Alright, metals, though, you can talk about. We know some things about metals. They are shiny, which we call lustrous. They are generally silvery, color-wise speaking. They are hard. They are ductile, meaning you can make wires out of them. They are malleable, meaning you can flatten them. And they're typically conductive to both heat and electricity. And we're going to see non-metals tend to be the opposite of all these things. Non-metals are dull. They are often colorful or colorless. These are brittle. And they are not ductile or malleable, and they are insulators. So they do not conduct heat or electricity very well. And so when you think about metals, metals are pretty easy. The iron, okay, shiny, silvery, hard. I can make wires, I can flatten it out, and it's conductive. If you think about non-metals, for example, sulfur, it's dull. It's this kind of pale yellow color. It's yellow. It's colorful. If you take sulfur and hit it with a hammer, it's just gonna shatter. Not even shatter. It's just gonna crumble. It's that sort of thing. And sulfur is not going to be conducting electricity or heat for you. Some nonmetals are like oxygen. Oxygen is blue. At least liquid oxygen is. These things are going to be kind of similar patterns here. Typically, most are most solids, or most metals are solids, with the exception of mercury. And non-metals are all over the place. Most are gases: oxygen, nitrogen, fluorine, chlorine, helium, xenon, argon, neon, all gases. A couple are solid, like sulfur, like carbon. Some are liquid, like bromine. And so we see that there's just some kind of patterns here. Finally, we also see that metals tend to form positive ions, stuff on the left there. Non-metals typically form negative ions. That's why we saw those groups on the right side of the periodic table tend to form negative things. Those groups on the left side tended to form positive things. All those transition metals have various positive charges. And the barking begins. And so we have kind of patterns here. Our semi-metals are in between on all of these. So silicon is a shiny, silvery, brittle, somewhat conductive solid that doesn't form ions at all. And silicon's a metalloid, right, or a semi-metal. So silicon is somewhere in between these. So it's got some metallic properties, some non-metallic properties, and it's gonna behave its own way. And so, same thing with boron. Boron is... I don't think I've ever actually seen boron. Let's Wikipedia it. Let's see what boron looks like. So boron is apparently also shiny and silvery, but it's going to be brittle, and it's going to be kind of not so conductive, and it's typically not going to form charged compounds, but it could. So it can do all sorts of things. So boron is another example of a a metalloid. So it does kind of different things. All right. Whew. We did a lot of vocab today, didn't we? All sorts of learning how to do names of things. Speaking of names of things, on Thursday, we're going to learn how to name compounds. So, make sure you have your polyatomic ions memorized by then, alright? That chart of stuff, try and have that at least handy by the time you watch Thursday's video. So, again, that's going to make things a lot easier when we have those in mind. So, we'll start learning how to name compounds on Thursday. Alright? So, we are good to go. I guess I'll see you Thursday, so just let me know if you have any questions. Alright, take care. Let's see if my face shows up. Nope, still the same. Okay, well, whatever. Alright, see you guys. Take care.